Hi friends, in the last lecture we had seen how the arithmetic expressions can be expressed in three notations: infix, prefix and postfix. We had also seen that even though the representation of arithmetic expression in an infix forms looks very simple and easy to use for human beings, but this notation has been found to be inefficient from the compiler point of view, as one has to remember set of rules like operator precedence and association rules, and a repeated scanning is required from left to right for the evaluation of the expression, which is quite inefficient. On the other hand, postfix and prefix notations are much easier to handle by the compilers, as there is no need of remembering operator precedence or any other rule. An important application of stacks is evaluation of arithmetic expressions written using infix notation. The problem of evaluating infix expression can be broken into two stages. First, infix to postfix conversion. Second, evaluating a postfix expression. For compilers, converting an infix expression into postfix expression and evaluating a postfix expression is a easier problem than directly evaluating infix expression. In the last lecture we had seen how a postfix expression can be efficiently evaluated using stacks. In this third and concluding talk on stacks, today we shall see how stacks can be used to convert infix expression to postfix and prefix notations. We first have a look at the algorithm for converting an infix expression to postfix. We shall be using a stack to store the operators and opening brackets. The postfix expression will be stored in a postfix string which is initialized to blank. The algorithm uses precedence of operators as shown in the following table. As it can be seen in the table, among the operators, the addition and subtraction operators have lowest precedence, followed by multiplication and division operators, while the exponential operator has highest precedence. For opening brackets, we have different precedences when they are present in the stack and when they are outside the stack. The opening bracket has highest precedence of the stack, which means that it will always be inserted without removing any of the operators on the stack, as it has highest precedence. Once the bracket is inserted in the stack, then its precedence becomes lowest, which means that it cannot be popped off by any operator. The complete algorithm is as follows. The infix string is scanned character by character from left to right. There could be 4 types of characters. The character could be an operand, an operator, or an opening or a closing bracket. If the character is an operand, then it is appended to the postfix string. If the character is an opening bracket, then it is pushed onto the stack. If the character is a closing bracket, then we repeatedly pop and append all the operators to the postfix string until an opening bracket is popped from the stack. The brackets are not appended to the string. If the character x is an operator, then we check the character y currently at the top of the stack. If the stack is empty or y is an opening bracket or y is an operator of lower precedence than stack, then we push x into the stack. If y is an operator of higher or equal precedence than x, then pop and append y to postfix string and then push x into the stack. When all the characters in infix expression are processed, then pop all the remaining characters from the stack and append them to the postfix string one by one. We now explain the algorithm with an example. Consider the following infix expression. We have an opening bracket, then a plus b minus c, then a closing bracket followed by star d minus opening bracket e plus f followed by a closing bracket. We now scan the infix string character by character from left to right. First, the opening bracket is encountered and it is pushed onto the operator stack. The next character a is an operand and it is appended to the postfix string. The next character is addition operator. The character at top is an opening bracket and so the addition operator is pushed onto the stack. The next character b is an operand and it is appended to postfix string. The next character is subtraction operator. The character at top of the stack is addition operator and as the precedence of addition and subtraction operators is same, so we pop the addition operator and append it to the postfix string. Then the subtraction operator is pushed onto the stack. The next character c is an operand and it is appended to the postfix expression. The next character is closing bracket and it causes all the stack elements to be popped till an opening bracket is encountered. The popped elements except the opening bracket are appended to the postfix expression. The next character is multiplication operator and it is pushed onto the stack as the stack is empty. The operand d is next appended to the postfix expression. The next character is subtraction operator. The character at top of stack is multiplication operator and as the precedence of subtraction operator is lesser than multiplication operator, so we pop the multiplication operator and append it to the postfix string. Then the subtraction operator is pushed onto the stack. The next character opening bracket is pushed onto the operator stack as it has highest off stack precedence. The operand e is next appended to postfix expression. The next character is addition operator. The character at top is opening bracket and as the precedence of addition operator is greater than opening bracket, so it is pushed onto the stack. The operand f is appended to the postfix expression. The next character closing bracket causes all the stack elements to be popped till the opening bracket is encountered. The popped elements except opening bracket are appended to the postfix expression. And finally, on reaching the end of the string, all the elements are popped and appended to postfix string. And finally, we have now converted the infix expression to postfix expression. We now next discuss the algorithm for converting an infix expression to prefix. This algorithm is quite similar to the earlier algorithm for converting infix to postfix, but it has a few extra steps for reversing the string. We shall again be using a stack for storing the operators and closing brackets. In addition, a prefix string is used to store the prefix expression which is initialized to blank. The algorithm is as follows. First, the infix string is reversed so that the last character comes at the first place and the character at the first position goes at last position. The reversing of string will also result in all closing brackets coming before their matching opening brackets. The reversed infix string is then scanned character by character from left to right. There could again be 4 kinds of characters. The character could be an operand, an operator, or a opening or a closing bracket. If the character is an operand, then we append it to the prefix string. If the character is a closing bracket, then we push it into the stack. If the character is an opening bracket, then we repeatedly pop and append to the prefix string all the operators and characters until closing bracket is popped from the stack. We then discard the 2 brackets. If the character X is an operator, then while operator stack is not empty and precedence of element at top of the stack is greater than precedence of X and element at top is not a closing bracket, then we keep on popping operators from the stack and append to the prefix string. At the end, we push X into the stack. When all characters in infix expression are processed, then repeatedly pop the characters from the stack and append them to the prefix string until the stack becomes empty. At the end, reverse the prefix string to get the final expression in prefix notation. We now explain the algorithm with an example. Consider the following infix expression: opening bracket a plus b minus c closing bracket star d minus opening bracket e plus f closing bracket. First of all, we reverse the infix expression so that the closing bracket comes before the opening bracket and all other characters are reversed. The rest of the operations will be performed on the string. We now scan the reversed infix string character by character from left to right. The first character closing bracket is pushed onto the operator stack. The operand f is then appended to the prefix string. The next character is addition operator and it is pushed onto the stack. The next character is operand e and it is appended to prefix string. On encountering the opening bracket, all the stack elements are popped till closing bracket is encountered. The popped elements except closing bracket are appended to prefix string. The next character is subtraction operator and it is pushed onto the stack as stack is empty. The next character operand D is appended to prefix string. The next character is multiplication operator, and as the precedence of multiplication is greater than subtraction operator, so it is pushed onto the stack. The next character closing bracket is pushed onto the operator stack. The next character is operand C and it is appended to prefix string. The next character is subtraction operator and it is pushed onto the stack as top element of stack is closing bracket. The next character operand B is appended to prefix string. The next character is addition operator and it has same precedence as subtraction operator, which is on the top of the stack, and so the addition operator is pushed onto the stack. The next character is operand A and it is appended to prefix string. The next character is an opening bracket and all the stack elements are popped till the matching closing bracket is encountered. The popped element except closing bracket are appended to prefix string. Then we reach end of the infix string, and next all elements of stack are popped and appended to prefix string. Finally, we reverse the reverse prefix string to get the final prefix expression. Friends, with this we now reach the end of our talk on stacks. Stacks, we have seen, are extremely simple data structures with numerous practical applications. We had seen with examples how stacks can be used by compilers for checking for matching brackets, conversion of infix expression to prefix and postfix expressions, and evaluation of postfix expressions. In our next lecture, we shall be starting with another simple data structure Q, which has many practical applications in operating systems and systems simulation. Thank you.